Okay, so let's take a look at an example here. So it says use the method of Frobenius to obtain at least one series solution about x equals 0 for the differential equation y double prime plus 3 over x y prime minus 2y equals 0. So let's first note that x equals 0 is a regular point, and the reason for that is because this would be your p function, this would be your q. Let's note that. Okay, so my p of x function would be the 3 over x, and my q of x function would be a minus 2. Well, q of x equals minus 2 is analytic already, so there's no need to check that. But 3 over x is not analytic at 0 because you're dividing by 0. But if I multiply it by x minus 0, my p guy will just turn into 3, and 3 is analytic. So therefore x equals 0 would be a regular singular point of this differential equation, so we can apply the method of Frobenius to find the series solution about x equals 0. We know there's going to be at least one of these series solutions. Okay, so let's write down this series. So the series will look like this, because we're centered at 0, so it's going to be x minus 0, just x here. It's going to be n plus r. We have to determine the a of n, we have to determine also. So the differential equation requires us finding the first and second derivative. So let's take the first derivative of this guy. So you'll take the n plus r in front and subtract 1. So doing that we get then. So I get this when I take the derivative. Again, I took the n plus r down in front and subtracted 1 from the power. Okay, and let's take the second derivative. So second derivative, I'll take this guy down now in front and subtract 1 from this power. So doing that we get then. Okay, so here's my second derivative. So I took the n plus r minus 1, in front here, multiplied it with the n plus r, subtracted 1 from the power. Okay, so now we're going to substitute the series up here into a differential equation. So doing that we get then. Okay, so I substituted the series into the differential equation up here. So I have my y double prime, which is this guy here. Then plus 3 over x times y prime, which is here, which I've written here. Then minus 2 times y, so it'll be minus 2 times my y, which is this guy here. I can now multiply the x in there. Well, this is like x to the minus 1 power, 1 over x. So when I multiply it in with this one, it's going to be a minus 2 up there, and I can multiply the 3 here and bring the minus 2 in here. So doing that we get then okay, so multiply the 3 over x in. So again, x is 1 over x you can write as x and minus 1. So he's going to subtract 1 from his power, which I've done here, and multiply the 3 here. And this guy, put a 2 over here. Okay, so now notice I'd like to combine these summations, but the problem is that this has x to the n plus r minus 2 power. So does this. This has a different power. So we're going to have to try and rewrite it so they all have the same powers here. So I'm out of space here, so let me erase a few things and we'll keep going. Okay, so here's what we have. Now, as I mentioned already, this guy has x to the n plus r minus 2 power, so does this one. This is n plus r, so this is 2 higher than these ones. This is minus 2, minus 2. This one doesn't. So we're going to have to try. We're going to have to lift these up too, each of these, so they all have the same powers on the x's. So in order to do that, we're going to make a substitution on these indices here. I'm going to say let n equals k plus 2 here and here. I'll explain why in a second now. So let me just write it here. Okay, it's going to let n equal k plus 2 here and in here. And this summation is going to let n equal k. Okay, so this one starts at n equals 0. So if I have the substitution n equals k plus 2, if n starts at 0, that means k would have to start at minus 2 because minus 2 plus 2 would be 0. So I'm going to put k plus 2 in place of n here, here, and here, here, and here. And I'm going to put k in place of n here and here. So doing that we get then. Okay, so making the substitutions, I'm putting k plus 2 in place of n here, 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 and here. So I've done it here. So it'd be k plus 2 in place of n, there will be k plus 2 plus r minus 1. So it'll be then k plus r plus 1. That's how I got that one. Then putting k plus 2 here in place of n, you'll have k plus 2 plus r, which you can write as k plus r plus 2, which I've written here. That's going to be a of k plus 2. And then it'll be x to the, so putting k plus 2 in place of n here, the 2 and the minus 2 will cancel, I'll just be left with k plus r. And then it's starting at minus 2 here because we have n equals k plus 2, and the smallest n can be is 0. So you put 0 on that side, you'd have 0 equals k plus 2. That means subtracting 2, k would have to be minus 2. So k is minus 2 here. And doing the same thing on this one then, that's how I got this. This also starts at minus 2 on your k. And over here, I'm just substituting n equals k up here. So it'd be the same thing, just replacing n's with k's. It's still starting at 0. Okay, now they all have the same powers on the x. X to the k plus r, x to the k plus r, x to the k plus r. But there is a problem still. This one starts at minus 2, this one starts at minus 2, but yet this one starts at 0. So let's note something here. So note here, if you had summation k equals minus 2 to infinity of b to the k plus 2 power, subscript here. So it says start at k equals minus 2. So sticking minus 2 in place of k here. So it'd be minus 2 plus 2. That'd be the k minus 2 term. Then after that, it goes up by 1 to be minus 2, minus 1, 0, 1, 2, and so forth. So after minus 2 it'd be k equals minus 1, so put minus 1 in place of k. And then you can think of as then starting at 0 and going to infinity. So pretty much you have the k equals minus 2 term, the k equals minus 1 term, and then 0 and going forward. So we're going to use that trick here. So we can think of the b k plus 2, say, as this one. Okay, so we can think of the b k plus 2 as this whole thing here, or this one here. So we're going to apply to both of those. So we're going to have the k equals minus 2 term, the k equals minus 1 term. So doing that we get then. Okay, so using this up here, so we're putting minus 2 in place of k here, 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 and here first. So putting minus 2 there, it'll be negative 2 plus r plus 1. Putting minus 2 here, negative 2 plus r plus 2. Putting minus 2 here, a minus 2 plus 2, and then putting minus 2 here, x to the minus 2 plus r. Then putting minus 2 here also, 3k, which is minus 2 plus r plus 2, a to the k is minus 2, x to the k, which is minus 2. Then we're going to put minus 1 in place of k next, so putting minus 1 here, which I've done here, minus 1 plus r plus 1. Then putting minus 1 here, minus 1 r plus 2, putting minus 1 here, negative 1 plus 2, putting minus 1 here, minus 1 plus r, putting minus 1 here, negative 1 plus r plus 2, putting minus 1 here, a to the negative 1 plus 2, putting minus 1 here. Then we can, like the note says, we can then start with the k equals 0 on these guys. So it'll be this guy now starting at 0, which I have here, and this one starting at 0, and this guy's still right here. Okay, we can simplify this a bit here because the minus 2 plus 1 is minus 1, so let me change this. And this is just r here. So let me just change these guys. So changing these guys we get then. So simplifying these terms up here then. So the k minus 2 term up here simplified to r minus 1 times r a0 x to r minus 2. The minus 2 term here simplified to 3 times r a0 x to r minus 2. Then the minus 1 term over here simplified to r times r plus 1 a1 x to the r minus 1. And the minus 1 term here simplified as 3 times r plus 1 a1 x to the r minus 1. Then we have these summations down here. Now they all start at k equals 0, all three of them. So we can actually factor the summation out in front, and they all have x to the k plus r also. Let's factor that out also. So doing that we get then okay, so I factor the summation out over here to write as one summation. I factor the x to the k plus r out over here, and the first two terms inside there actually had a to the k plus 2 in common. I factored that over here also. So I can write the series like this. Okay, so I'm out of space here, so let me erase a few things and we'll keep going. Okay, so we have it here. Now to solve this, since it equals 0 on this side, all the coefficients in front of the x's need to be 0. But before doing that, let's simplify it a bit further. So for example, here we have a x r to the minus 2 here and here. Let's factor it out. Let's also factor an r out on these two. And these ones, let's factor the x to the r minus 1 out. Let's factor the r plus 1 out also. And the one down here, they both have k plus r plus 2 here and here. Let's factor that out in front also. So doing that we get then okay, so again on these first two here I pulled a 0 out and an r out. So pulling an r out, there's an r minus 1 left there and a 3 left there, and r minus 1 plus 3 would be r plus 2. That's how I got that. So these first two here simplify to this. And these over here, these two, I can pull an r plus 1 out like I've done here. To be an r left and a 3, so it'd be r plus 3, a1, x to the r minus 1. And these guys here, I pull out the k plus r plus 2 here and here. I pull that in front here. There'll be a k plus r plus 1 left here and a 3 left here. But a 3 and 1 make 4, so I get the 4 here. So it simplifies like this. And as I mentioned, we now, all the coefficients have to be 0, so that has to be 0, that has to be 0, this has to be 0. So equating coefficients we get then. So equating the coefficients then, so each of the coefficients in front of the x's must be 0, so the r times r plus 1, a0 is 0, the r plus 1 times r plus 3, a1 is 0, and this guy is 0 for k greater than or equal to 0. Okay, note here now, to make this, we have freedom over the choice of r. If I chose r to be 0, say, it would make this equation true, but it would not make this would not be 0, but we have freedom over the a1 and a0 also. So let's make an assignment here. So let's make the following assignment. So say we let r be 0, a0 be 1, and a1 be 0. Then that would make this equation true because r is 0, that would make this equal to 0. And now a1 being 0 would make this equation true. You can see there's other choices I could have chosen here, and they may lead to a different answer. Because remember, Frobenius' method says there exists at least one series solution. So this should lead to a series solution, this assignment here. Okay, alright, so just justify to yourself that these assignments make these two guys 0. Okay, now we need to make this guy 0 also over here. Let's solve it for ak plus 2. So let's add 2ak to both sides and then divide by this guy to solve for ak plus 2. So doing that we get then. So first I move the 2ak over here, and let's divide now by this guy to solve for ak plus 2. Doing that we get then. Okay, so solving for ak plus 2 we have this. And this is for k larger than or equal to 0 up here. Okay, so we have r0, a0 is 1, a1 is 0, and this recursive definition here. Because it's recursive because you need to know AK. So for example, if K was 0, then you have to use A0 then to find A2. So putting 0 there, A0 then would equal 2 over this thing would equal our A2. So this is a recursive definition. So we're going to have to solve this recursive relation here. Okay, but this video is getting kind of long, so I'm going to leave it here, and we'll pick up on this on part 2 in the next video. Okay, so we're going to pick it up at this point in the next video. Alright, so let's leave it there.